So now we're going to add one more element to this and allow ourselves to compute factorial, which is really a sequence of these operations where we continually subtract 1 from n, or n minus 1, then n minus 2, then n minus 3. We're going to go through that sequence. And we want to continue doing that, okay, until the cycle at which the decrement that we're about to do is going to produce a 0. So we're going to be looking at the output of the decrementer, and as soon as the b minus 1 is 0, we want to stop. We don't want to do any more multiplications. Meanwhile, we're accumulating the product of a times b, and a is sort of the accumulator, the thing that's keeping track of the product so far. We take that intermediate accumulated value and we multiply it by the current value of the B register, which is, as I say, is being, sort of B is the value of n being decremented cycle after cycle. The thing that we've added here, in addition to the control logic generating the control signals, is the ability for the control logic to sense some state from the data path, to sense the status of the data path. I shouldn't have used the word state. Sense some status from the data path. In this case, and so that would mean that we can now make our entire machine, it can have data-dependent operations. In other words, the dependency in this particular case is we can do something different when b minus 1 is equal to 0, and we can cause the machine to stop what it's doing and start a new operation. And so this sort of combination of not only generating control signals, but listening carefully to the status of the data path allows us to perform a wide range of data-dependent computations, which is really what your computer is all about. So, and so this is a very, very simple example of control signals going to the data path and status signals coming back. So what we're going to do is to actually compute factorial. We'll redraw the control structure here, where in fact we're going to loop in state 1 as long as the z signal is 0. And if we go back and look at the other diagram, the z signal is the thing that's telling us whether b minus 1 is 0. And so when z is 1, b minus 1, the value is equal to 0. And when z is 0, b minus 1 is still some positive integer. So what we'll be doing is sort of staying in state 1, causing the data path to loop and loop and loop and loop and loop, to cycle after cycle, sending it the same control signals until finally we detect that b minus 1 is equal to 0, and then we're going to be done. And the answer we want then will be in the A register. So what I've done here is to factor in the use of the z signal in building my control ROM, which I've represented in tabular form. And in fact, the only thing the z signal controls is the choice of the next state. So when I'm in state 1, and in state 0 and in state 2, the z signal has no effect. It's only when I'm in state 1 does the value of the control signal determine what the next state is. Notice the control signals are the same. They're independent of z. It's only the choice of the next state that differs. Everybody sort of happy with this as a machine that will actually loop through many, many, many cycles, slowly computing factorial for us? I mean, it's a fairly simple little device. And the thing that makes our device data dependent is the status signal that's coming back from the control logic. Okay, so what we've given ourselves here is a little programmable engine where we have a data path that's being controlled by this FSM, and the FSM generates a bunch of control signals each cycle that affect what the data path does. And the data path listens to some status signals to change what it will do depending on whatever the status signals are indicating is happening inside the data path. So this is sort of a little cycle of I send you control signals, you're the data path, you send me back some status signals, then I, the control logic, determine what state I'm going to go to next and change how my control signals are going to work. You say, okay, well, is this really a computer? And well, sort of not. I mean, if you think about what we wanted in terms of an abstract model for computation, we needed something that had more than just finite storage, and so in fact, 2 registers isn't going to cut the mustard. It actually can only load a couple registers and perform fixed arithmetic operations, so it's not really programmable in any way. Its program is fixed, so we're going to set about trying to remedy that.